Hello, everyone. I'm Dale Geis, a security architect at Gigamon, here to present a session for Bootcamp 2020 on decryption architectures, HSM, and certificate management integrations. Before we jump right into the content, I do want to present a few definitions and terms that will be used. At the top, DSSL represents the Gigamon standard passive decryption. ISSL represents inline decryption that relies on a man in the middle, or MITM. We'll talk about forward secrecy, perfect forward secrecy, as well as a HSM security module, which may use a remote file system in RFS. And the three C terms at the bottom are associated with certificate management and certificate authorities. And I also want to make sure that we're on the same common terms with regard to keys and certificates. So TLS sessions are negotiated using public key cryptography, which involves a private and a public key pair. The private key obviously needs to be kept secure. That's used by the crypto engines to perform all the crypto operations. But the public key is freely distributed as part of a digital certificate or a TLS certificate. So the point is, a key pair is made up of a private key and a certificate. And when you make a TLS connection, the server returns a certificate and the client uses that to authenticate the server. And the way that's done is because the certificate is signed by a certificate authority or a CA, and that establishes trust. The client trusts the certificate authority, and if the server returns a certificate that's signed by a trusted authority, then the session is good and there are no browser warnings or pop-ups. But it's important to note that these certificates have a max lifespan of about a year nowadays before they expire. And that's mostly to prevent private keys from being cracked. So the life expectancy is a year, maybe even shorter for certain CA services. So that means that a certificate renewal is required before that expires. And the point I want to make is that renewal involves not only the certificate, but also the new creation of a private key. So when a renewal occurs, it's the key pair that must be updated, as we'll see going through today's session. For decryption architectures, the focus of this session is for inbound deployments, meaning external users connecting inbound to web servers in a server farm, a data center. And I'm going to take a particular look at a passive decryption for multi-tier architectures. Starting simply, passive decryption involves tapping traffic or making a copy. It's not inline. A copy of traffic is made. It's pretty straightforward. That's fed to the Gigamon DSSL engine where it's decrypted and supplied to external systems. And in this inbound mode, the keys from the servers are actually replicated on the DSSL engine so that when users are connecting in from the outside world, the same keys are used and there are no trust issues. It's really just spoofing the server and making it look like the user's connecting to the server. And the decryption decision in the Gigamon product was based on associating a key with a server IP up to release 5.8. But since then, starting in 5.8, if you install the certificate also, then that automates that process where when a session is detected, the certificate is used to determine which key to use and decryption can happen without the need to configure the server IPs, which is a lot easier. And this works for servers in physical, virtual, cloud, containers, pretty much anywhere because we just need to get a copy of the traffic and feed it out to that engine. Now, to contrast that with an inline solution, the inline solution, the ISSL engine, actually sits in line with the traffic in a bump in the wire mode. And it intercepts traffic, detects TLS sessions, and then performs that decryption as a man in the middle. And when it does that decryption, it then uses service chains to feed that traffic to inline tools where it decrypts, sends the unencrypted traffic to one or more inline tools, receives the traffic back from those tools, re-encrypts, and sends it on its way. Also, while it's decrypted, a copy can be made to send it off to forensic or packet capture stores or other out-of-band consumers of that traffic. And again, the local key pairs are copied onto the decryption device from the servers, and the server spoofs that connection or spoofs the server for the incoming connection, and everything looks normal to the outside world. Now, not all traffic is always decrypted. Their decryption decisions are based on configurable policy. So there are oftentimes when passive decryption is desired, maybe it's just, there's no need for an inline tool where the desire is to just decrypt and make a copy, or for other reasons, maybe it's not allowed in certain environments. And so passive decryption is possible, but it really is only possible in this inbound mode that I'm describing here, because the private keys are required to do passive decryption. And those private keys are only available in, if you own the servers, if you control the servers. Now also, passive decryption does not work with what are known as forward secrecy or perfect forward secrecy ciphers, which is exclusively what TLS 1.3 uses. Really, the only cipher that is primarily used for decrypting are those that use the RSA key exchange or key transport algorithm. That's because with the private key, and if this key exchange algorithm is used, it is possible to capture the traffic and derive the necessary session keys to be able to decrypt the traffic. Yeah, inline decryption involves the man in the middle, really a decryption proxy or a TLS proxy. And that is what's required for forward secrecy-based ciphers, especially TLS 1.3, and that supports any mode. The inbound that we're talking about, or also an outbound where your users are connecting outbound to the internet, and as well as any arrangement for internal deployments. And it does introduce a little bit of certificate and trust management, or some requirements there. That's pretty well-known science. We'll talk about that in a minute. And it does also offer something called passive inline. You may sit inline to do this decryption and gain visibility into these perfect forward secrecy-based ciphers, but then really only make a copy and feed it to an out-of-band consumer. It doesn't predicate the need to have an inline tool just because you're doing inline decryption. So what about the case of a multi-tier web application? If we were to consider doing inline SSL decryption in a multi-tier application, it would pretty much involve decrypting between the different tiers. Because these environments today, all of this traffic is encrypted on the wire. Some years ago, it may be decrypted once by the load balancer and flow between these tiers in the clear, but that's not the case anymore. Traffic on the wire is encrypted, and that would, create issues, mostly because doing inline SSL decryption in each of these tiers would add latency and complexity for that decrypt, re-encrypt each time. And so passive decryption is really desired in this type of environment. I've had a number of conversations with customers in the recent months about this type of architecture. And the desire is something like this, really, to be able to tap that traffic between the tiers, feed it to the passive decryption engine, decrypt that traffic, and then feed it to applications for monitoring, for security, for troubleshooting, for a variety of different reasons. And the benefits to this type of architecture should be obvious. There's no inline insertion, there's no added latency, and you can gain this multi-tier visibility. Challenges, of course, are those that I mentioned with out-of-band decryption in general. Can't decrypt perfect forward secrecy, which means no TLS 1.3 or any of the Diffie-Hellman ephemeral or elliptical curve, Diffie-Hellman ephemeral, any of those ciphers that have that DHE in them. That E means ephemeral, and that means you can't decrypt them passively. And it does introduce then a per tier key and certificate management requirement. So what about using why is this perfect forward secrecy such a demand? And why aren't non-PFS ciphers considered for decryption? Well, obviously, to the outside world, going across the internet, I think it's clear we want to have the strongest ciphers possible. But what about inside the organization? So I took a look at PCI DSS, the latest standard 3.2. something, and it addresses a number of things, but R3 talks about stored cardholder data, and R4 talks about the encryption, the transmission of cardholder data across open public networks, where this needs to be encrypted. But it doesn't specifically address the transmission of this data across internal private networks. So it's very specifically talking about open public networks. And in general, they don't actually define what should be done and what's acceptable. They defer to industry standards like the NIST 800 series of special publications. So if you then look at 852 latest Rev, and again, this is geared towards government entities, but commercial industry also looks largely to NIST for a lot of guidance. So you can take this with a little grain of salt, but it's pretty legitimate. They encourage TLS 1.3 and require all servers to support it by the end of 2023. And they're pretty much saying don't use TLS 1.0 and lower now, and very select use of TLS 1.1 only were required. They're also sunsetting TLS RSA key exchange because it's deemed not as strong as the other available options. And of course, then they're proposing ephemeral keys, the Diffie-Hellman ephemeral, liquid curve, Diffie-Hellman ephemeral. But they also talk about regular Diffie-Hellman, not ephemeral, which would have a static key exchange just like the TLS RSA key exchange. But they don't preclude that, which sort of perplexes me. Maybe it's an oversight, maybe just the thought that Diffie-Hellman is more secure than RSA, but quite honestly, the static certificate DH key exchange is no more secure than RSA, and quite, in fact, with the latest Raccoon vulnerability, we should not even be considering the Diffie-Hellman static. So with this in mind, I think there's a viable architecture that uses a combination of approaches to maintain strong crypto out on the public open internet, yet at the same time support passive decryption in an enterprise security zone. And those are the two zones that are shown here. The public TLS zone is the outside world, the internet, and the enterprise TLS zone is that inside private network zone. So the idea here is that facing the public, we would of course want to use perfect forward secrecy-based ciphers, TLS 1.3, etc. Yet on the inside, a hardened TLS 1.2 using RSA key exchange is still a viable option, in my opinion, with strong crypto. And that would enable the passive decryption between these tiers while still using very strong crypto into the outside world. So I believe, based on PCI DSS and its reliance on its language about open public networks, that this is an architecture that could still be PCI DSS adherent. And that split proxy is something that Gigamon is currently working on in our ISSL engine. The ability to configure this engine to have different profiles for these two zones so that we can run TLS 1.3 and strong crypto in the outside and run TLS 1.2 and the RSA key exchange internally in the enterprise zone so that that could then be passively decrypted and fed to the out-of-band devices and security tools and network monitoring and troubleshooting. So the potential challenges here, even though I believe it's viable, there might be some pushback from certain compliance auditors or compliance organizations who just look at the standard and say, this says this, it's got to be this, without really reading and thinking about what it means. So there could be some problem there. If FIPS 140-2 level 3 is a requirement, then we may have to introduce HSM technology into this environment. I mean, that really doesn't differ, you know, for this particular architecture. If FIPS 140-2 level 3 is a requirement, then an HSM is a requirement anyhow. But you know, we could have lots of key pairs to deal with here, hundreds and thousands of servers, which really means a certificate management platform would have to be in play to make this achievable. And this slide puts that together in terms of what a representative architecture might look like. This is by no means what an exact architecture might look like. I named a couple vendors here. It doesn't mean it would have to be those vendors or only those vendors. It's just these are a couple vendors that you know, Gigamon integrates with. So I've mentioned them here. And the idea of this CMP, this certificate management platform, could be, you know, an internal system, could be a product like Venati, would take a role in managing all of these certificates and performing the updates and renewing the certificates and pushing all of those certificates out to the various decryption engines, as well as the servers that are in play here. And the HSM could be in play for storing the keys. The HSM may have what's called an RFS, a remote file server, for sharing key tokens. And you know, all of that correlation is done by the CMP. But this, you know, this would be an architecture that I think still provides strong crypto. I could argue that it adheres to PCI DSS and likely other compliance requirements, and sort of gives you the best of both worlds. So the next section is to then dive a little bit more into the HSM and certificate management platforms and what they do in the current Gigamon integration. They are different products, but they do functionally overlap in quite a number of areas, and that often causes confusion. You know, I have conversations with folks who are talking about HSM doing, you know, certificate management functions, and certificate management products doing HSM functions. And again, that's because there is some overlap there. But the fundamental purpose of an HSM is to safeguard digital keys, you know, provide some key management and crypto operations. Whereas the certificate management platform is primarily, its primary purpose is around automating the lifecycle management for certificates and keys. If you recall that certificates and keys really go together as a key pair when we talk about pushing this crypto material out to systems that need to use them. And there are some representative vendors here, you know, a couple that we see all the time in our customer base. That doesn't mean that these are the only ones, again, just a representative list. The motivation of an HSM, it stems from the security risks associated with manual creation and the unsecured handling of private keys. So there's a big push in especially financial institutions and other industries to really eliminate the manual handling of private keys. And so HSMs for generating and storing those keys, if you will, is, you know, a big part of that motivation. And as I mentioned, if you have a FIPS 140-2 level 3 compliance requirement, that essentially dictates that an HSM technology needs to be in place. Certificate management platforms, on the other hand, you know, their motivation stems from the thousands of servers that can potentially exist in a large enterprise and large server environment, where, you know, there may not be really good inventory of all of these certificates. So they focus on discovering and maintaining an inventory of certs tracking the expiration dates to ensure timely renewals, and then distributing the renewed certs/key pairs to the various entities and automating this whole process. So if we then step into an HSM, I think one of the concepts that may be a little foreign to folks is that HSMs don't actually store raw private keys. And you may be scratching your head at this statement, but what I mean by that is, you can use OpenSSL or some technology to create a raw key, the raw key that the actual crypto device would use. But in the HSM world, if that key is created on the HSM or created externally and submitted to the HSM, that key gets wrapped. And it's wrapped to produce what is called a key token. It's an encryption that's done by the HSM using its super secret key, deep inside the HSM that never sees the light of day. So it can encrypt a key, create a token, and then that token is the wrapped private key with some metadata and some access control. And only that HSM or HSM in the same cluster, if you will, can decrypt that. It's because they use symmetric encryption decryption. The same key, that same super protected key inside the HSM can encrypt the key to create a token and then take that token and decrypt it to derive or reproduce that private key. So that's why I say a private key is never actually stored. It's the token that's stored, and it's the internal operation of the HSM that can extract that private key. So that really means that tokens can be shared and are generally shared and stored outside of the HSM, not in the HSM. And in the Encipher HSM case, there's something called an RFS, a remote file system, that's used for that purpose. These HSMs create these tokens, they're stored in an HSM, and then the clients who need access to these tokens can retrieve them from the RFS. Now, as far as the Gigamon integration, as of the 5.9 release, it looked pretty much like this. A customer process was involved to create the keys, create the key tokens on an HSM, and then those key tokens can be loaded on the DSSL engine. Then whenever the need exists to decrypt a session, we determine which token to use, send that token via a dedicated crypto API to the HSM. The HSM takes that token, produces the private key, does some math, generates some session keys, and sends them back to the DSSL engine so it can then go ahead and decrypt that session. So again, the private key or representation thereof is the token that the client or DSSL engine in this case holds, and it interacts with the HSM to generate the necessary session keys to do that decryption. With the latest 5.10 release, we've added support for the RFS and using an RFS sync function to now connect and pull key tokens onto the DSSL engine platform. So that simplifies the process in a bit, that there's no need to actually push these tokens specifically to the Gigamon device. They can be put in the RFS where that is then shared with other clients, including the servers that may require these key tokens, and it can automatically pull them, and then the rest of the crypto API remains the same, where we would use that token to interact with the HSM to get the session keys to decrypt the session passively. Moving on to certificate management platforms. Now, the CMP is not a term you're going to find if you search for it. It's just something I use because certificate-related platforms have a number of different names and acronyms they go by. But really the important concept of a certificate management platform is certificate lifecycle management. So as I mentioned, there are many resources out there in the environment that may have certificates and keys, and it may not be very well documented or inventoried. And that's one of the features that many CMPs provide. They go out and discover certificates that exist in the environment and then store them into a certificate store, which may also be a key store if there's a key vault involved, as we've talked about. And then it monitors those certificates, looking for the need to refresh them. Typically, if the certificate expires, but sometimes they could be externally revoked. And so it would monitor, make a notification to the owners. The owners could then come back and kick off an update, or this could be automated where the CMP would automate the update, getting a new certificate from an internal or external CA, put that back into the store, and then ultimately provision these renewed key pairs out to the crypto resources. So obviously, it's a pretty broad scope, right? And not all vendors do all of these functions. Some don't do discovery, some don't do provisioning. So you really have to, when we talk about certificate management, we really have to understand which aspect. For example, Gigamon, the primary part of CLM that we're concerned with is provisioning. It's that one slice, because it's important to make sure that those key pairs are provisioned from the CLM onto the Gigamon device so that it can continue to perform its decryption functions with renewed certs and not run into expiring situations. I mentioned HSMs may be involved here, where the certificate manager interacts with an HSM, or it could use a key vault, again, which is essentially storing a tokenized representation of that private key. So I think it's important here to understand that when we talk about certificate management, it has many meanings. And so we have to be certain to understand which aspect of CLM we're talking about. And in the Gigamon world, that's primarily around the provisioning side. And how that would look with a Gigamon integration to Venati something like this diagram. The GigaView Fabric Manager, the box represented by GigaView FM, is our overall product or overall orchestration and management platform for all of the Gigamon components, hardware, software, virtual, etc. And it exposes an API for this certificate bulk provisioning. And so an external system like the Venati Trust Protection Platform would do all of that certificate management, certificate lifecycle management, do all of those functions such as generating key pairs, renewing key pairs. It may interact with an HSM. It stores the certificates, maybe the keys in the vault, as we've talked about, and ultimately bulk provision those out through the Gigamon GigaView FM API, which in turn steers that information out to one or more of the GigaView HC decryption devices. So and the HC decryption devices have a key vault in them also, so that they basically store a token version of the key once it's pushed out. There are some cases where certain platforms may do a pull instead of a push, go to the Venati Trust Protection Platform to pull the crypto information, but in this model, it is a push driver. And so the Gigamon driver is available from the Venati marketplace. It was released in release 5.9 and is available to support these environments where there are large numbers of certificates, especially for these inbound scenarios where there are hundreds or thousands of servers. So that is a look at the TLS decryption architecture, primarily passive versus inline. Well, we discussed passive versus inline, but we primarily focused on passive today. and the need for visibility in multi-tier applications, but the complexities of doing so in the forever push mode of the industry, wanting to go with TLS 1.3 and strong crypto, what that looks like and what that means in terms of a public open network versus a private closed network. The concept of a split TLS, which is something that we're implementing in our inline SSL solution. And then how to manage all of this by potentially, housing the keys or using an HSM for key tokens and using a certificate management platform to coordinate and automate the key renewal, certificate renewal, and bulk provision. Thank you for attending and have a great day. If you have any questions, certainly please reach out to the organizers or reach out to your Gigamon representative and I can follow up. And I do want to say thank you and also give a plug to the Gigamon community, which is an outstanding resource. It's a community where you can go to gain information, more deeper technical information and product information about Gigamon products, ask questions that are answered by Gigamon experts as well as your peers in the industry. In fact, I was once at a customer location and there was a question about a product feature that I wasn't sure the answer, and the customer went online and said, well, according to the Gigamon community, the answer is this. But that was a pretty good example of the value of the Gigamon community. So if you don't have an account, please go sign up today, and thank you again for attending.